should have a number on
On to chapter 5. All right. Newton came up with 3 laws of motion. The first one, or this is officially the second law of motion. He did not word it like this. His was more along acceleration is proportional to the force. That's closer to Newton's wording, except he did it in Latin. But in essence, F equals ma is Newton's second law of motion, abbreviated as N2L. Now, what's the formula for acceleration?
velocity over change of velocity over time.
You just wrote it right there.
Yes, I did.
Force divided by mass.
So if acceleration is 0, what else must be true?
The displacement, not displacement, but the change in velocity is also 0.
Okay.
Or no time has elapsed.
That would be like indeterminate. Yeah.
Whoa!
Yeah, you
I
can't have
believe
motion
Yeah.
Later, y'all.
Bye.
I
Have a
don't
beautiful
deserve to be
time.
here.
You'd have 0 over 0, which, as everyone knows, is equal to a constant. Sorry, I had a physics professor once say that. I understood what he meant. It was not a literal thing. That was just more of a limit
Yes.
thing. But that's not what he said. All right, so change in velocity is 0. What's the other thing that must be true?
Direction.
What about the direction?
There is none.
That there's
It could be.
no force being
If
the
the
position
direction of
changes.
what, I guess, comes down to? Direction of whatever?
Position.
Direction of, the direction of, the velocity is constant. The position direction would have to change.
Yeah.
Sorry, say that again. If velocity is constant, then the direction of the position cannot change. All right. I wasn't going that far, because you can also have situations where if the position direction is not changing, yet you still have acceleration.
Right.
What force is that? In Newton's second law, what is, when they have rate F equals ma, what does F represent besides force?
Kilograms per meter.
Stop.
That's sharp too. Newton's.
I was gonna say like the total force.
Yes.
The force, yeah, the force.
Total force. We don't write total force or net force usually, but it's supposed to be understood that that's the total force. I'll write it explicitly here. The total force is 0, the change in velocity is 0, acceleration is 0. If one of these is true, the other two are automatically true. So if the change in velocity is 0, that means it has a constant speed and direction. The speed could be 0 or not. So if the total force acting on something is 0, that means that whatever the speed is, it's going to maintain that in whatever direction. It's not going to change direction. It won't change the value of the amount of speed. In other words, an object that's moving in some particular direction at some speed will keep doing that unless the total force isn't 0. Or as is commonly said, an object in motion will stay in motion, an object at rest will stay at rest at a constant velocity unless acted on by some net outside force. So that's what I just worded there somewhat quickly is Newton's first law. An object at rest, ... That's Newton's first law, which is just the long wordy version of Newton's second law. I'm not quite sure why he differentiated. And Newton's third law we've done already. I just didn't call it that. But
Not certain why you differentiated.
yeah, Newton's first law and second law to me, or second law is a more explicit. The first law is just writing out the words.
Yes.
Have you read Bush?
I've read parts of.
As I understand that,
Translation of
he
it.
didn't necessarily state it in 3 distinct laws, but over time, physicists that, you know, have restated
I was
it.
pretty sure he had a 1, 2, and 3.
1, 2, and 3?
Yeah. I've got afterwards, if you're interested, we can track it down. All right. We last left off, I believe we had just done box on ramp.
Yes. I think we did both force stuff. We did box on ramp with pulley and.
No, I'm talking about actually, we went through the problem with the box on cliff and other one falling. We got to the end of that one.
Yeah.
Yes.
We got to a kid.
And then,
We had a child and a sled and a.
Yeah, we did the.
after that, yeah, so we got that far. We did not do ramp, okay.
Wait, are we doing
Okay,
kill?
so here it is.
We did.
The box on ramp on Polion?
No, what I'm talking about is, we got past the force diagrams.
Yes.
You are all expert on the force diagram. Sure. Yeah.
I guess that's what we're calling that.
Thank you for the comment.
We have a ramp that's attached to the ground. I have a box on the ramp. Acceleration of box equals. We're in the process of going through the technique that I'm trying to teach of how to solve a slew of these problems. And so we did object on cliff, another one falls, what's the acceleration of the system? And so now we're gonna do a box fall going down a ramp, what is the acceleration of the system? At this point, we're gonna let the coefficient of friction be 0. The symbol right here is coefficient of friction. Coefficient of friction. In other words, I'm making the claim that it's frictionless. This is just shorthand notation. It's a frictionless ramp. The angle down here is theta. Now, I'm gonna put, it has a mass m, but ultimately the mass is irrelevant here, and we'll show why. And we're gonna go through the steps. The facades method.
No, we wrote it down. But yeah.
We've
I know
applied
what you
it
mean.
once.
Yeah.
All right, so force diagram. We have box, we have ramp. What can we get rid of? All right, so there is no mysterious force thrown into the problem.
Not seeing any tension,
All right,
and that's about it. I suppose.
we can actually get rid of one more for this problem.
Oh, friction, because.
There isn't any.
Yeah.
Coefficient of friction is
Frictionless.
0.
All right, so we're left with these two forces involved. We have normal force and gravitational force. Which way is the gravitational force acting?
Straight down towards the center of the presumed planet.
And what do we call this gravitational force?
Weight.
W.
And so we have this weight acting up, and then which way is normal force acting on the box?
Perpendicular to the surface of contact.
Like that.
Yeah, right, there we go.
Like that.
Again, called normal force, because normal means perpendicular. All right, so we have these two forces acting on it. So force diagram done. A for acceleration. What is the direction of the acceleration of the box if it accelerates?
Down.
And so, now oftentimes, just based upon the physical nature of it and our just common knowledge, we can figure out the direction of acceleration. If we don't know, it becomes a lot more complicated, but you see those problems for the test. So the acceleration is down the ramp. So we know the acceleration. CA, the coordinate axes. When we establish our coordinate axes, we want one of them to be in direction of acceleration and one of them to be perpendicular to that. So I'm going to establish my I and j direction here, I had the direction of acceleration and j had either away from the ramp or towards the ramp. It really doesn't matter. I'm just gonna do it that way. Or I guess over here would redraw it. They are perpendicular to each other. Coming up with a coordinate system where they're not perpendicular to each other is much more advanced physics. All right, questions to hear? Because last time we didn't decompose, we're about to decompose something. Any questions to hear? All right, D for decomposition. So the question is, I got my two vectors here acting on the mass. Are either of these vectors not completely in a positive or negative j direction or positive negative I direction?
The weight.
Yes. So weight is what we need to decompose. We need to break the weight up into how much of it is in the I direction, how much of it's in the j direction. That is the triangle that we are doing. Now to figure out, this is a right angle here. One of these angles is theta. So let's figure out which one is theta. So I'm going to just draw I know weight is acting down this way. I know this angle here is theta. I am breaking it up into my perpendicular components. Some students will want this, the one down the ramp to go all the way to the bottom of the ramp, and they basically try to break it up into components like that. Not perpendicular. It is possible to do it that way. It's just, you've now quadrupled the amount of math you have to do.
You did it. Congratulations.
So if this is theta here, what is this angle here?
The complement of the angle's 90, and that's theta, so it must be 180 minus theta minus 90.
90 minus.
Or simplified. Now I'm going to label this theta prime as the complement. It is indeed the complement. For those who need the structure of it, theta plus theta prime is equal to 90 degrees. I know that this angle right here is 90 degrees because weight is acting straight down. So if this is theta prime here, what is this angle here?
Theta prime minus 90.
Or 90 minus theta prime,
90 minus theta.
which is just theta. So in my angle here, this one down here, this angle here is the same as this angle here. The opposite side is the one dealing with sine, the adjacent is cosine, so the one down the ramp, this angle right here, or this vector right here, must be W sine theta. And this one right here is W cosine theta. So
We're using the angle right there, kind of like at that and like, which angle are we using?
this angle right down, that angle right there, that's theta. That's this angle right here. So I'm making the claim that my force diagram with the two black arrows there is the equivalent to the following force diagram. I have y going this way. I have the weight times the sine of theta going down the ramp, weight times the cosine of theta going into the ramp. My force diagram with the black arrows there is the equivalent of this. And on the lab on Thursday, this is the theoretical force down the ramp. And that's the theoretical normal force. Oh, we'll get to that in a second. So decomposition, done. Any questions on the decomposition?
So what exactly designates that that angle will be theta?
Basically working through it this way.
I see the 90 degrees, I see the original theta, and then I see theta prime.
So that's the complement.
The complement.
This, since weight is acting straight down, that's a right angle there, and that's a right angle there. Those two angles have to add up to 90 degrees. And since that's the complement of theta, that has to be theta. Or, as I established earlier, you said yourself, this angle was the complement.
It is.
Theta plus theta prime is equal to 90 degrees.
Correct.
Suppose we don't know that, so let's say that this is phi. We'll call it phi for right now.
Mhm.
I know that phi plus theta prime is equal to 90 degrees. Because that's a right angle, therefore that has to be a right angle.
Uh-huh.
And so therefore phi is equal to 90 degrees minus theta prime.
Right.
Hey, theta equals 90 degrees minus theta
But
prime.
there's only one other number plus theta prime that would end up equaling 90,
Yep,
which is theta.
yes. That's the justification.
I hear you. And understand.
Now, there is an alternate method, because, you know, we get into a test and suddenly you panic.
All the time?
Whenever I draw my angles, they almost always look like 45 degrees. So just sort of think through it. Suppose theta is really small. Suppose theta is about 10 degrees. So if I drew that proportion, tried to draw that properly, I got a small angle right there. Almost all of the force is, I have weight acting down, almost all of it is going to be, let's see if I can draw that bigger. My weight is acting down, and I'm breaking it up into components here. Just drawing it proportionally, I see that this is bigger than that. So if my angle is under 45 degrees, this is going to be bigger than that. If I know one of them is going to be the weight times the sine of theta, and the other one's going to be weight times the cosine of theta, I can just look at it, get them both, and go, well, the bigger one is this, the smaller one is that. If it's steeper, say something like that, so theta is 90 degrees. Well, all the weight is vertical, so you can do sine of theta and cosine, sine of 90 degrees and cosine of 90 degrees. Sine of 90 degrees, well, that's the one down the ramp. Cosine is the other one.
Doesn't matter.
Well, it does.
But
It's zero.
All right, so we have the diagram like that. Now the equations. What is the base equation for which all of these will be written?
Force equals mass times
F
acceleration.
equals mass times acceleration.
Come on.
Equals-
How many equations will we have?
We'll have two, one for the y component and one for the x component of force.
You've been brainwashed. What are the two equations?
The J will be I and J.
Yes,
And,
there's no x or y.
Ah, interesting.
I've taken calculus at the same time as this. So I have.
Now, if you want to do x hat and y hat, go for it, but I didn't. So there.
Uh,
All right, so we have an I hat equation and we'll have a J hat equation. It's very similar to what we did when we did projectile motion problems, we just usually didn't call it I hat and J hat. All right, so my I equation, I said down the ramp was positive, so we write down all the positive I hat direction vectors,
W sine theta,
minus all the ones in the negative direction,
none.
okay? Equals mass times acceleration. I don't have to put a vector symbol over the A because we've already established the acceleration is going to be down the ramp. And so the magnitude is A, the direction is I hat. Now the J hat direction.
Was positive J hat is the normal force
Cosine theta.
subtracted from
Minus.
the normal force acting.
You worded it wrong, but I assume this is what you meant.
Subtracting the normal force from the
Okay.
box.
Oh,
No, subtracting as well, no?
what are we subtracting from what?
So that
Yes.
y going into the ramp isn't gonna get subtracted.
We're looking at this right here.
Oh, all right.
So y minus w cosine theta equals mass times, well, what is the acceleration in the j hat direction?
Zero. So, it's just,
One of the reasons for establishing our coordinate system this way is so that one of our equations is equal to 0. And so we can rewrite this, well, actually, we'll get to that in just a second. So those are the equations, done. Substitution. We have several things here. Do we have a formula for anything here?
We now have a formula for.
I heard M. That's what I thought I heard. Do we have a formula for anything here?
For Y?
We have a formula for Y?
Y equals W cos theta.
I'm talking general formula that's always true.
No.
Is that a nod yes, or, I saw some movement, that was a nod no. Okay.
I mean, sort of.
Well, hint, we actually do have an equation.
For the next year, but.
Sorry? For what? Oh, we tend not, we don't want to do that formula. Yes, that is, we could do dv dt, but we're solving for A.
And
So we're solving for A, we don't want to do that formula. Somebody just say it?
M.
What formula are you thinking?
I'm just guessing.
All right, spoiler, weight.
It's Mg.
Yes, weight is equal to mg.
Mg.
So if I have an object in free fall, so it's just falling, I have only one force acting on it. Weight. If I plug into F equals ma, my weight is equal to mass times the acceleration due to gravity. That's the formula right there. So whatever I've got weight, I can write in mg. And so these equations become mg sine theta. That is getting sad.
me too.
All the time.
There we go. Mg sine theta is equal to mass times acceleration, and y is equal to mg cosine theta. So in the lab, when I talk about the theoretical normal force, it's going to be mg cosine theta. So from this equation right here, we can simplify it, mass cancels out, and our formula for acceleration is just g sine theta. So if it is a 30-degree angle, so theta is 30 degrees, and g is 9.8 meters per second squared. And by the way, g is always a positive number, again,
So-
unless you're dealing with anti-gravity.